Time is something we all experience every day. Seconds tick by, minutes slip away, and years pass almost without notice. But what if I told you that the flow of time is not the same everywhere? That time itself can stretch, slow down, or even almost stop, depending on where you are and what's around you. This is not science fiction, this is reality. Time is flexible, and the force that governs its rhythm in ways we cannot see is gravity. For centuries, humans believed that time was absolute. Isaac Newton, one of the greatest scientific minds in history, imagined time as a constant river, flowing uniformly for everyone, everywhere, independent of motion or matter. According to Newton, a second was the same on Earth, in the sun, or on a distant star. Time was immutable, a universal clock ticking steadily across the cosmos. But at the start of the 20th century, Albert Einstein challenged that fundamental idea. His theories of relativity revealed something astonishing. Time is not a fixed, unchanging backdrop. Time is intertwined with space, forming a single four-dimensional fabric we now call spacetime. And just like a sheet of rubber stretches or bends under weight, spacetime can warp and twist under the influence of mass and energy. Gravity is not just a force pulling objects together. It is the bending of spacetime itself. This bending has profound consequences for the way time flows. Imagine placing a heavy ball on a stretched rubber sheet. The ball causes the sheet to dip around it. If you roll a marble near the edge, it curves inward toward the ball. In a similar way, massive objects like planets, stars, and black holes curve space-time around them. And just as the path of the marble is affected by the dip in the sheet, the flow of time itself is affected by the curvature of space-time. Clocks in stronger gravitational fields tick more slowly than clocks in weaker fields. Time, in essence, is relative to gravity. To grasp this, let's step back to something a little closer to home. On Earth, the difference is imperceptible in daily life. A clock on the ground ticks ever so slightly slower than a clock on top of a tall building. It's a minuscule effect, measurable only with the most precise instruments. But it exists, and it is a hint of a far stranger reality waiting for us in the depths of space. As we look further into the cosmos, the effect grows more dramatic. Near a neutron star, a collapsed core of a massive star so dense that a sugar cube-sized piece would weigh billions of tons, time itself slows dramatically. And near a black hole, where mass is concentrated into an infinitely dense point called a singularity, time slows to almost a standstill. An astronaut hovering just outside the event horizon, the point of no return, would experience seconds while years or even centuries pass. For someone far away, this isn't just theoretical. We see the consequences of time's flexibility in our daily technology. The satellites orbiting Earth, forming the backbone of the global positioning system, must account for both their speed and the weaker gravitational pull they experience in orbit. Without correcting for these relativistic effects, GPS devices would drift by kilometers every single day. Time is not a constant. It is a variable, stretching and contracting in ways that shape reality itself. Understanding how gravity warps time also challenges the way we think about the universe. It forces us to confront a reality where the universe is not a static stage, but a dynamic, ever-changing fabric. The flow of time is not uniform. It is sculpted by the invisible contours of gravity, invisible yet undeniable. Every massive object, from planets to stars to galaxies, leaves its mark on space-time, subtly altering the rhythm of the cosmos. In this series, we will explore how gravity bends time, from the smallest effects in our own solar system to the extreme warping near black holes. We'll see how this phenomenon is measured, how it affects our technology, and how it shapes the universe on a cosmic scale. By the end, you'll begin to see time not as a steady, predictable river, but as a living, breathing dimension, one that twists, curves, and flows according to the invisible hand of gravity. So buckle up. We are about to step into a universe where time is not what it seems, where seconds can stretch into minutes, and where the ticking of a clock is shaped by the mass and gravity of the world around it. This is the story of how gravity warps time, and it begins with the realization that reality itself is far stranger and far more beautiful than we ever imagined. Before we dive fully into how gravity warps time, it helps to understand another piece of the puzzle: how motion alone affects time. This is the domain of Einstein's special relativity, a theory that turned our intuitive understanding of space and time upside down. It tells us something astonishing. The faster you move, the slower your clock ticks. Time is not absolute. It is relative, depending on your motion. Imagine two identical twins. One stays on Earth living a normal life. The other boards a spaceship and travels at near the speed of light, racing across the galaxy. When the traveling twin returns, something incredible has happened. The twin who stayed on Earth has aged decades, while the traveling twin has barely aged at all. This is not science fiction. This is a real consequence of the universe's rules. It's called time dilation, and it arises because the speed of light is always constant. Einstein realized that the laws of physics are the same for everyone, no matter how fast you are moving. But the speed of light is a cosmic speed limit. It cannot be exceeded. To make this work, the universe stretches and compresses time and space. Clocks moving at high speeds run slower, and distances along the direction of motion shrink. This is why astronauts traveling near light speed would experience time differently than people on Earth. You don't have to travel to distant galaxies to see this in action. Even in our own solar system, the effect is measurable, though subtle. Atomic clocks on fast-moving jets or orbiting satellites tick slightly slower than identical clocks at rest on the ground. It is a tiny difference, but it proves the principle. Motion itself changes time. Time is not a universal constant. It depends on your frame of reference. Special relativity also reveals that energy, mass, and motion are deeply connected. The famous equation E equals mc squared. This equation is a direct result of this theory. Mass and energy are interchangeable, and this relationship is at the heart of how the universe behaves at high speeds. It also sets the stage for our next step: gravity. Because if motion alone can warp time, what about the more powerful, invisible influence of mass and gravity? The transition from special to general relativity is subtle but profound. Special relativity applies in the absence of gravity or in regions of space where gravity is negligible. But the universe is full of massive objects, planets, stars, black holes. And each of these objects exerts a gravitational pull that affects not just motion, but the very structure of space-time. To understand how gravity warps time, we first had to understand that time is flexible to begin with. Motion taught us that time is relative. Gravity would take this lesson even further. To illustrate, think of a spaceship moving at incredible speed near a distant star. Time aboard the ship slows compared to an observer on the planet. Now imagine that instead of moving, the ship hovers near a massive star. Even without moving, time aboard the ship still runs more slowly than it would far away from the star. This is the bridge between special and general relativity. Time slows not only due to speed, but due to gravity. Special relativity also gives us the tools to grasp extreme scenarios. In the thought experiment of the twin paradox, the traveling twins experience seems paradoxical only because our intuition treats time as absolute. Once we accept that time is relative, the paradox disappears. Similarly, once we accept that gravity bends space-time, the strange behavior of time near massive objects becomes understandable, even if it feels surreal. Finally, special relativity forces us to reconsider our deepest assumptions about reality. Past, present, and future are not universally agreed upon. They depend on your frame of reference. Two observers moving relative to each other can disagree on the order of events. Time is not a simple, linear progression. It is a dimension that interacts with space, motion, and eventually gravity. The universe does not march forward uniformly for all observers. It flows differently depending on where you are and how you move. This understanding is essential before we can explore how gravity warps time. Special relativity shows that the universe's clock is flexible, that seconds are not sacred and immutable, and that the closer we move to nature's speed limit, the more time itself bends. It sets the stage for the next revelation. That gravity, the invisible curvature of space-time caused by mass, also warps time, and in ways that can be far more extreme than anything motion alone can produce. In the next part, we will step into Einstein's theory of general relativity, where mass, energy, and gravity come together to shape the fabric of space-time itself. We'll see how planets, stars, and black holes bend time around them, creating phenomena so strange that they challenge everything we thought we knew about reality. Special relativity taught us that time is relative. General relativity will show us that time can be stretched, slowed, and twisted by gravity itself. If special relativity taught us that time is flexible depending on motion, general relativity teaches us that time is flexible depending on gravity. Einstein's insight in 1915 revolutionized our understanding of the universe. Gravity is not just a force pulling objects together. It is the bending of space-time itself. Massive objects like planets, stars, and black holes warp the very fabric of the universe, and this warping affects the flow of time. To visualize this, imagine space-time as a stretched rubber sheet. Place a heavy ball in the center, and the sheet dips under its weight. Roll a marble near the edge, and it curves toward the center, not because there is an invisible force tugging on it directly, but because the sheet itself is curved. In this analogy, the marble follows the contours of space-time just as planets follow curved paths around stars. Gravity is the manifestation of this curvature. But it's not just space that bends. Time bends too. Clocks run more slowly in stronger gravitational fields. The closer you are to a massive object, the slower your time passes relative to someone far away. This is called gravitational time dilation, and it has been measured directly. Even on Earth, the difference is tiny but real. A clock at sea level ticks just a fraction slower than a clock atop a mountain. This effect becomes extreme near neutron stars or black holes, where time can stretch almost to a standstill for an outside observer. The principle underlying this idea is known as the equivalence principle. Einstein realized that being in a gravitational field is locally indistinguishable from being in an accelerated frame of reference. Stand in an elevator accelerating upward, and the force you feel is identical to gravity. This simple but profound insight allowed Einstein to generalize special relativity to include gravity, creating a theory that describes how mass and energy curve space-time and how that curvature governs the motion of everything within it. Consider a planet orbiting a star. Newton's laws describe the motion accurately for most everyday cases, but Einstein's equations show the deeper truth. The planet is not pulled by an invisible force. It is moving along a curved path in the warped fabric of space-time created by the star's mass. Mercury's orbit, for example, precesses slightly differently than Newton predicted. General relativity explains this discrepancy precisely, confirming the warping of space-time. Time dilation due to gravity is not just a theoretical curiosity, it shapes our modern world. GPS satellites orbit Earth at altitudes where gravity is weaker than on the surface. If their clocks ran without correction, GPS positions would drift by kilometers each day. Engineers must account for both special relativity because the satellites move quickly, and general relativity because the gravitational field is weaker than on Earth. Without these corrections, navigation systems would fail. Einstein's equations also predict more extreme scenarios. Neutron stars pack the mass of the Sun into a sphere barely 20 kilometers across, creating a gravitational field so intense that time slows significantly for anyone near them. Black holes take this to an even more dramatic extreme. Near a black hole's event horizon, gravity is so strong that time appears to almost stop relative to a distant observer. An astronaut hovering there would experience minutes, while years pass for someone far away. In this way, general relativity unites space, time, and gravity into a single dynamic system. Time is no longer an immutable backdrop, but a dimension that bends and stretches, shaped by mass and energy. The universe is not a static stage, it is a living fabric, constantly shifting, with every massive object leaving its mark. The consequences of this are not just abstract or mathematical. They define how matter moves, how light travels, and how the universe evolves on every scale. In the next part, we'll explore gravitational time dilation in more detail, examining how time slows in the presence of massive objects and how this effect has been observed and measured, from Earth-based experiments to the extreme environments around black holes. We will see that the warping of time is not just a theory, it is reality, measurable and profoundly strange, challenging everything we think we know about the flow of time. Now that we've seen how mass warps space-time, it's time to focus on one of the most astonishing consequences of this warping: time dilation caused by gravity. In simple terms, the stronger the gravitational field you are in, the slower time passes for you relative to someone farther away. This effect is not a prediction of science fiction. It's a measurable, real phenomenon. And while it's subtle in our everyday experience, it becomes mind-bendingly extreme in the presence of dense objects like neutron stars and black holes. Let's start with a simple analogy. Imagine two identical clocks, one sitting at the top of a tall tower and the other at the base. Gravity pulls more strongly at the base than at the top. If you wait long enough and then compare the clocks, the one at the bottom will have ticked just a tiny bit slower than the one at the top. The difference is minuscule, barely detectable with ordinary instruments, but it exists. This is gravitational time dilation at work, and it confirms that time is not universal. It is relative to the gravitational field. This effect grows stronger as the mass and density of an object increase. Consider a neutron star, the remnant of a massive star that has exploded in a supernova. A neutron star contains more mass than the Sun, compressed into a sphere barely 20 kilometers across. The gravity near its surface is so intense that time itself slows dramatically. An observer far away would see processes near the neutron star occurring in slow motion. For anyone near the star, life would feel normal, but from the outside, seconds might stretch into minutes or hours. Black holes take this effect to the ultimate extreme. The event horizon, the point of no return around a black hole, is a boundary where gravity is so strong that time essentially stops for a distant observer. Imagine an astronaut hovering near the event horizon while a friend watches from a safe distance. To the distant observer, the astronaut appears to move in slow motion, their every action stretched out indefinitely. For the astronaut, however, time feels completely normal. This stark difference between perspectives illustrates just how relative time can be under intense gravity. Gravitational time dilation is not just theoretical. It has been measured in numerous experiments. In the 1950s, the Pound-Rebka experiment confirmed that light loses energy as it climbs out of a gravitational field, effectively showing that time runs slower in stronger gravity. Today, we rely on atomic clocks to detect the tiny differences in ticking rates between Earth-bound clocks and those flown in airplanes or orbiting satellites. The results are precise and consistent, matching Einstein's predictions down to fractions of a second. The implications of gravitational time dilation are profound. If you were to travel near a massive object and return, you could effectively leap into the future relative to everyone who stayed farther away. This is one-way time travel made possible by the universe's rules, not by science fiction machines. Near extremely dense objects, what feels like hours to you could be decades or centuries to someone observing from afar. Even in our solar system, this effect matters. GPS satellites orbit Earth at altitudes where gravity is slightly weaker than at the surface. Without correcting for gravitational time dilation, along with the time dilation caused by their orbital speed, GPS signals would drift by kilometers each day. Engineers must account for both effects to keep navigation accurate, a practical, everyday demonstration that the bending of time is not just theoretical, but affects technology we use daily. Gravitational time dilation also forces us to rethink the nature of reality. Time is not a constant river flowing uniformly for all observers. It is a flexible dimension, bending and stretching according to mass and energy. Every massive object in the universe leaves its mark on time, subtly or dramatically altering its passage. From towers on Earth to black holes in distant galaxies, the flow of time depends entirely on the curvature of space-time around you. In the next part, we'll explore black holes and the extreme warping of time in more detail, delving into what happens at the edge of an event horizon and how these phenomena have been observed. We will see time dilation not just as a small effect, but as a dramatic, almost surreal distortion of reality itself, a window into the true strangeness of the universe. If gravitational time dilation around planets and stars is remarkable, black holes push the phenomenon to a level that almost defies comprehension. Black holes are regions of space-time where mass is concentrated into an incredibly small volume, creating a gravitational field so intense that nothing, not even light, can escape. And in the presence of this extreme gravity, time itself behaves in ways that are utterly surreal. To understand this, let's picture an astronaut approaching a black hole. As they draw closer to the event horizon, the boundary beyond which escape is impossible, time begins to stretch dramatically relative to a distant observer. A few seconds for the astronaut might correspond to years, decades, or even centuries for someone watching from far away. From the outside, the astronaut appears to slow down, moving ever more slowly as they near the horizon, eventually seeming to freeze in time. But for the astronaut, their own time flows normally. Their watch ticks as usual, their heartbeat continues, and they remain unaware of the immense dilation unfolding relative to the rest of the universe. This extreme time warping arises because the curvature of space-time near a black hole is so severe. General relativity tells us that the stronger the gravitational field, the slower time passes. A black hole represents gravity taken to the extreme. Near its singularity, the infinitely dense core at the center of the black hole, the curvature becomes infinite, and the mathematics of time begins to break down. We call this a singularity not just because of density, but because the laws of physics as we know them cease to provide meaningful predictions. Visualizing this effect can be mind-bending. Imagine looking through a telescope at a spacecraft falling into a black hole. As the ship approaches the event horizon, the signals it sends back arrive more slowly and are stretched in wavelength, shifting toward the red end of the spectrum. The ship appears to move in slow motion, its descent seemingly frozen, while the universe beyond continues at its normal pace. For an external observer, it is as though time itself is stopping at the edge of the black hole. But the story gets even stranger. If the astronaut could somehow survive the immense tidal forces near the event horizon, they would witness the outside universe in a kind of accelerated time-lapse. Stars would age rapidly, galaxies might evolve in what feels like hours, and the distant cosmos could change in ways that would normally take millions of years, all in a short, subjective period for the astronaut. Gravity doesn't just slow time locally, it warps the perception of time across the universe relative to that position. These effects are not merely theoretical. Observations of matter spiraling into black holes, particularly in X-ray binaries and active galactic nuclei, show the consequences of extreme gravity on light and time. Matter falling toward a black hole emits energy, but its radiation is stretched and delayed in ways that match the predictions of gravitational time dilation, and the detection of gravitational waves from black hole mergers by observatories like LIGO further confirms that space-time itself is flexible, stretching and rippling under enormous mass and energy. Black holes also provide a natural laboratory for thought experiments about the nature of time. Could an observer hovering near a black hole use time dilation to travel into the distant future? In principle, yes. Even a brief visit to the edge of a supermassive black hole could allow someone to experience hours, while the universe outside ages by decades. Of course, the practical challenges of surviving such an environment are immense, but the physics itself makes the scenario plausible. Ultimately, black holes reveal the true extremes of gravitational time warping. Time is not absolute. It is a dimension molded by mass and energy. Near ordinary stars, clocks slow slightly. Near neutron stars, the effect becomes dramatic. And near black holes, time stretches almost to infinity, challenging our intuitive understanding of reality itself. The universe, in these extreme regions, behaves in ways that are profoundly alien, yet governed by the precise, elegant rules of general relativity. In the next part, we'll explore gravitational lensing and time, showing how gravity not only bends light, but also subtly affects the timing of events across the cosmos, providing even more evidence of the profound connection between mass, space-time, and time itself. So far, we've explored how gravity slows time near massive objects, from planets to black holes. But gravity's influence on the universe goes even further. It not only stretches time, it also bends space and the path of light itself, a phenomenon known as gravitational lensing. And as we'll see, this bending of light is intimately connected to the warping of time. Imagine space as a flexible fabric. Place a heavy star or galaxy on this fabric, and it creates a depression. Light traveling nearby follows this curve, bending around the massive object instead of traveling in a straight line. To a distant observer, the light may appear distorted, magnified, or even duplicated. This is gravitational lensing, a cosmic mirage created by the curvature of spacetime. Einstein predicted this over a century ago, and today astronomers routinely observe it in distant galaxies, quasars, and clusters of matter. But the story doesn't stop at bending light. Time itself is affected by the same curvature. When light passes through a gravitational field, it experiences what's called a Shapiro delay. Radar signals or photons take slightly longer to travel near a massive object than they would if space were perfectly flat. This delay is a direct consequence of time running slower in a gravitational field. Light doesn't speed up to compensate. Instead, it follows the warped space-time, and in doing so, its travel time is stretched. A classic example comes from observations within our own solar system. In the 1960s, scientists bounced radar signals off planets like Venus. They noticed that signals passing near the Sun took longer to return than expected. This wasn't a mistake, it was a clear measurement of the Shapiro delay, confirming that the Sun's gravity warps space-time and slows time. Every photon traveling near a massive body experiences this delay, illustrating that gravitational time dilation and spatial curvature are inseparable aspects of the same phenomenon. Gravitational lensing also allows us to glimpse the distribution of mass in the universe. Some of the lensing effects we observe come not from visible matter, but from dark matter, the invisible substance making up most of the universe's mass. By mapping the way light bends around galaxy clusters, astronomers can infer where mass exists, even when we cannot see it directly. And because the curvature of space-time affects both space and time, these observations also provide indirect evidence of how time itself is warped across cosmic distances. Consider a distant quasar, billions of light-years away, whose light passes near a massive galaxy cluster before reaching Earth. The quasar may appear as multiple images or arcs. The light that takes slightly longer paths arrives delayed, sometimes by days, months, or even years. In other words, gravitational lensing can not only bend light, but also stretch time itself, creating a natural cosmic delay. Observing these delays allows astronomers to measure distances, masses, and even the expansion rate of the universe, all by exploiting the warping of space-time. This connection between light, mass, and time deepens our understanding of the universe. Time is not a separate, independent dimension. It is inseparable from space and gravity. Every photon, every planet, every star moves through a space-time landscape shaped by mass. Gravitational lensing is a striking visual and practical demonstration of this truth. The universe is a dynamic fabric where both the path of light and the flow of time are intertwined. In essence, observing gravitational lensing is like peering into the structure of space-time itself. It shows us that time is not uniform across the cosmos. It stretches and slows where mass is concentrated, subtly altering the arrival of light and signals. From black holes to galaxy clusters, from the bending of starlight to the delayed echoes of distant quasars, the warping of time is everywhere, quietly shaping the universe in ways that we are only beginning to fully understand. In the next part, we'll turn from these cosmic scales to the experiments that measure gravitational time dilation directly. From atomic clocks on airplanes to precision tests that confirm Einstein's predictions, these experiments prove that time warping is not just theory. It is a measurable reality, observable both in the heavens and here on Earth. So far, we've explored the strange ways gravity can warp time, from slowing clocks near planets to freezing them near black holes. But these are not just theoretical ideas. Over the past century, scientists have repeatedly confirmed gravitational time dilation through careful experiments, some on Earth, some in orbit, and some at the far edges of the cosmos. These experiments show that Einstein's predictions are not just abstract mathematics. They describe reality. One of the earliest confirmations came in the 1950s with the Pound-Rebka experiment. Scientists wanted to test whether gravity could change the frequency of light, a direct consequence of time running differently at different heights. They sent gamma-ray photons from the bottom of a tower to the top. According to Einstein, the photons should lose energy as they climb out of Earth's gravitational field, because time runs slightly faster at the top. When measured, the frequency shift matched predictions almost perfectly, proving that gravity does indeed alter the flow of time. Later experiments extended this work using atomic clocks, the most precise timekeeping devices ever created. In 1971, 2 atomic clocks were synchronized. One stayed on the ground while the other flew aboard a commercial airplane. After the flight, scientists compared the clocks. The airborne clock had ticked slightly faster than the one on the ground, exactly as predicted by general relativity. Even though the differences were measured in billionths of a second, they clearly showed that time is flexible and responds to both motion and gravity. Atomic clocks in orbit provide an even more striking demonstration. GPS satellites orbit Earth at altitudes of around 20,000 kilometers, where gravity is weaker and orbital speeds are high. Without relativistic corrections, the clocks on these satellites would drift by about 38 microseconds per day, enough to throw GPS positioning off by kilometers in just 24 hours. Engineers must adjust the satellite clocks to account for both gravitational time dilation and the time-slowing effects of their orbital velocity. This is everyday technology proving Einstein correct. Without accounting for warped time, your phone wouldn't know your location accurately. Even on a larger scale, astronomers observe time dilation around massive objects in space. Pulsars, rapidly spinning neutron stars emitting beams of radiation, serve as cosmic clocks. When a pulsar is in a binary system with another massive object, its pulses arrive slightly delayed due to gravitational time dilation. By carefully measuring these signals, scientists can confirm how gravity stretches time in ways consistent with general relativity. Gravitational waves also provide indirect evidence of time warping. When 2 massive black holes merge, they create ripples in spacetime that travel across the universe. Detectors like LIGO can measure these ripples with incredible precision. The waves themselves are a stretching and squeezing of spacetime, a direct consequence of the same curvature that slows clocks near massive objects. These observations offer further proof that time and space are inseparable and that mass fundamentally warps both. These experiments collectively leave little room for doubt. Gravitational time dilation is real. It is measurable, predictable, and consistently verified across a wide range of scales, from atomic clocks in laboratories to pulsars billions of light years away. Time is not a universal constant. It is a dynamic dimension shaped by mass and energy, stretching and compressing according to the curvature of space-time. Understanding these experiments also emphasizes how interconnected the universe is. The same principles that govern black holes and distant galaxies affect the clocks in our satellites and even the timing of signals on Earth. Gravitational time dilation is not some exotic curiosity. It is a fundamental property of reality, shaping the behavior of matter, light, and life itself. In the next part, we'll explore the philosophical implications and what-if scenarios of warped time. From the possibilities of one-way time travel to the ways our perception of reality is shaped by the flexible flow of seconds. Gravity warping time is not just a scientific fact. It is a concept that challenges our most basic assumptions about life, the universe, and the passage of time itself. Up until now, we've explored the physics of time, how it bends, stretches, and slows under the influence of gravity. But these phenomena do more than just reshape our understanding of clocks and satellites. They challenge the very way we perceive reality. Gravitational time dilation forces us to reconsider what time is, how it flows, and even how we might interact with the universe on scales far beyond human experience. One of the most fascinating consequences is the idea of one-way time travel. We've seen that near massive objects, like neutron stars or black holes, time slows dramatically. In theory, an astronaut could orbit close to a supermassive black hole for what feels like a few hours, then return to a distant location and find that decades or centuries have passed there. Unlike the science fiction concept of traveling backward in time, this is time travel into the future. It is not a fantasy. It is a direct consequence of general relativity. Gravity allows a form of temporal relocation simply by positioning oneself in the right region of space-time. This realization brings deeper philosophical questions. If time is relative and flexible, is there such a thing as a universal now? When the astronaut emerges from near a black hole, the world they left has aged far beyond their own experience. Simultaneously, the idea of simultaneity, that two events happen at the same moment, is called into question. Two observers in different gravitational fields or moving at different velocities may disagree about the order or duration of events. Reality, in this sense, becomes subjective, shaped by the observer's location and motion. Time dilation also forces us to think about the scale of human experience. In our daily lives, we assume time flows uniformly. A minute is a minute, a year is a year. But the universe operates on scales where this assumption fails completely. Near a black hole, 1 minute could correspond to centuries elsewhere. On a neutron star, a single day might stretch into months for a distant observer. Our sense of time is local and limited. The cosmos operates on a far more elastic timeline. Understanding this can be unsettling, but it also inspires awe. There are also profound implications for aging and life itself. Consider the astronaut orbiting a black hole. For them, life continues normally. They grow older, experience events, and perceive days and nights as usual. But the rest of the universe advances far faster. From the astronaut's perspective, their loved ones, societies, and entire civilizations could age beyond recognition while they remain unchanged. Time dilation transforms not just physics, but the human experience of life, mortality, and memory. Gravitational time warping also affects how we think about the universe as a whole. If time flows differently in different regions, then the history of the cosmos is not uniform. Stars, galaxies, and black holes evolve according to local conditions, and time itself is a dynamic variable in cosmic evolution. There is no single clock ticking for the entire universe, only a network of clocks, each influenced by the mass and gravity around it. This realization changes how we consider cosmology, causality, and the flow of events across billions of light years. Finally, time dilation invites us to embrace the mystery and strangeness of reality. The universe does not conform to our intuitive expectations. Clocks can tick differently depending on where they are. Seconds can stretch or contract in ways that defy everyday logic. Gravity, mass, and motion shape time itself. The cosmos is far stranger, more intricate, and more beautiful than our ordinary experiences allow us to perceive. As we move forward in this series, we will continue to explore how these phenomena manifest on a cosmic scale, from neutron stars and black holes to galaxy clusters and the universe itself. But for now, it's important to pause and reflect. Gravity warping time is not just a scientific concept. It is a lens through which we can see the universe differently, challenging our deepest assumptions and inviting us to expand our understanding of reality itself. So far, we've explored gravitational time dilation near planets, stars, and black holes, and even touched on its philosophical implications. But to fully grasp the power of gravity warping time, we must look at the universe on a cosmic scale. Across vast distances, from dense neutron stars to clusters of galaxies, time stretches and compresses in ways that challenge our everyday intuition. Consider a neutron star orbiting another star in a binary system. Neutron stars are incredibly dense, packing more mass than the Sun into a sphere just a few kilometers wide. The gravitational field near their surface is immense. A clock placed on or near a neutron star would tick noticeably slower than a clock located even a few thousand kilometers away. To a distant observer, the neutron star's seconds are stretched, its hours elongated. This isn't theoretical. Astronomers observe pulsars, rotating neutron stars, with extraordinary regularity. By measuring the arrival times of their pulses, scientists can detect minute differences caused by gravitational time dilation. These tiny differences reveal the extreme warping of space-time in these compact systems. Now expand the view further. Galaxy clusters, some containing thousands of galaxies bound together by gravity, are among the most massive structures in the universe. The cumulative mass of these clusters warps space-time not just locally, but across millions of light-years. Light from background galaxies traveling through these clusters is bent and delayed, an effect we call gravitational lensing. These delays are not just optical tricks, they represent real differences in the passage of time. Photons are taking longer to travel because time itself is stretched by the massive cluster's gravitational field. On a cosmic scale, the universe is a patchwork of time flowing at different rates, sculpted by the distribution of mass. Black holes, especially supermassive black holes at the centers of galaxies, take this effect to extremes. Near their event horizons, time slows almost to a standstill. Imagine a spacecraft orbiting a supermassive black hole like Sagittarius A star at the center of the Milky Way. A few hours for the crew could correspond to centuries for observers far from the black hole. If humans ever approached such objects, we could witness a form of natural time travel into the distant future. This is not science fiction, it is a real consequence of space-time curvature. Even light from distant stars carries evidence of time's flexibility. As it passes near massive objects along its journey, its speed may remain constant, but its travel time is extended by the warping of space-time. Gravitational time dilation is baked into the cosmos, affecting everything from the smallest particles to the evolution of entire galaxies. The universe is not just expanding spatially, it is a dynamic arena where time itself is stretched, contracted, and warped depending on the mass and energy it encounters. These cosmic-scale examples also highlight the relativity of simultaneity. Two events that appear to happen at the same time for one observer might be separated by years for another observer in a different gravitational field. Across the universe, there is no universal clock ticking for all observers. Instead, time is local, sculpted by mass, motion, and energy. The history of stars, galaxies, and clusters is not uniform. It depends on their local environment, their proximity to massive objects, and the curvature of space-time around them. In essence, looking at the universe on a cosmic scale reveals that time is not a single uniform river. It is a flexible, dynamic dimension, stretching and bending across space. From neutron stars to supermassive black holes to galaxy clusters, gravity shapes the very rhythm of the cosmos. Every second, every photon, every orbit is influenced by mass, energy, and space-time curvature. Time is no longer absolute. It is a living, breathing aspect of the universe, intricately linked to the cosmic landscape itself. In the next and final part, we will conclude our journey, reflecting on the full implications of gravity warping time, from the smallest clocks on Earth to the most massive structures in the universe, and consider what this tells us about the true nature of reality. After exploring the universe from the perspective of time, motion, and gravity, one truth becomes clear. Time is not a fixed, universal flow. It is a dynamic dimension intricately shaped by mass, energy, and motion. Gravity warps time. It slows it near massive objects, stretches it across cosmic distances, and in extreme cases can nearly freeze it entirely. The flow of seconds is not uniform. It bends and curves along with space-time itself. We began with the familiar, clocks on Earth, the slight difference between the top of a tower and the ground beneath. Subtle effects, almost imperceptible. Then we expanded our view to orbiting satellites, which must account for time dilation to keep GPS systems functioning. Even these everyday examples demonstrate that gravity warping time is not a thought experiment. It is an observable reality that affects our lives every day. From there, we ventured into the extraordinary. Neutron stars, pulsars, and black holes reveal time behaving in ways that challenge our very intuition. Near these objects, a minute can stretch into hours, a day into decades, depending on your vantage point. Time is no longer a steady river, but a flexible medium, bending under the influence of mass and energy. The universe itself is a tapestry where each region experiences time differently, sculpted by the gravitational contours of nearby objects. Gravitational lensing and Shapiro delays demonstrate that time warping is not confined to extreme environments. Across billions of light-years, light from distant galaxies travels through regions of curved space-time, taking longer paths than it would in a flat, massless universe. Time is subtly stretched as light journeys across cosmic landscapes, and the effect is measurable. Observations of these phenomena have revealed not just the presence of visible matter, but the invisible scaffolding of dark matter, further confirming that time, space, and mass are inseparable. Experiments on Earth and in orbit, from atomic clocks to radar signals, have repeatedly verified Einstein's predictions. The mathematics of general relativity matches reality with astounding precision. Time is elastic, responsive to gravity and motion, and the universe behaves exactly as Einstein described over a century ago. This is more than theory. It is fact. Time is flexible, and we live in a cosmos that constantly reminds us of this truth. The philosophical implications are profound. Our intuition tells us that time flows uniformly, that seconds, minutes, and hours are immutable. Yet reality is far stranger. Two observers in different gravitational fields may experience the same interval differently. Events that seem simultaneous to one may be separated by years to another. Life, aging, and the universe itself unfold at variable rates depending on location and mass. Gravity warping time challenges the notion of a universal now and invites us to see the cosmos as a web of relative experiences rather than a single absolute timeline. As we step back, the picture that emerges is awe-inspiring. Time is not a passive backdrop for events. It is a participant in the cosmic story, shaped by matter and energy, intertwined with space, bending and stretching across the universe. From tiny variations on Earth to extreme warping near black holes, from the pulsations of distant neutron stars to the lensing of light across galaxy clusters, gravity writes the rhythm of reality itself. Ultimately, gravity warping time reminds us that the universe is stranger, more beautiful, and more intricate than we can perceive in our daily lives. Every second, every photon, every heartbeat is influenced by the invisible structure of space-time around it. We are living in a universe where the flow of time is a local, relative, and dynamic property, and understanding this brings us closer to grasping the true nature of reality. As you reflect on this journey, consider the possibilities. Traveling near a black hole, witnessing the universe age faster than your own experience, or simply marveling at the fact that the clocks in your satellites run differently from those on Earth. Gravity warping time is not just a scientific discovery, it is a window into the fundamental workings of the cosmos, revealing a universe far more fluid, intricate, and extraordinary than we ever imagined. The universe is vast, full of wonder, and always moving in ways we are only beginning to understand. Take a moment to imagine your own place in this vast, time-warped cosmos. And remember that every tick of the clock is a dance with gravity, space, and the very fabric of reality itself. Thank you for joining us on this journey through gravity and time. The cosmos is vast, full of mysteries, and constantly revealing its story in ways we are only beginning to decode. We'd love to hear your thoughts. Leave a comment with questions, ideas for future videos, or what fascinates you most about the origins of the universe. Take care and never stop exploring.